Jason's head might be in the way. Can you see the whiteboard? Because I might be drawing on the whiteboard too. Yeah, actually, yeah, from here. Because I need to draw a list box and arrows and so on. Okay, all right, thanks. So yeah, pointers are basically just memory addresses. And so when you have a variable like int n, okay, that's a variable. It has 4 bytes, and there are 4. This is my memory. Okay, it's 16 gigabytes or 32 gigabytes. So that's the memory of my computer. Now n is a variable and it's an integer. How many bytes does an integer take up? 4 bytes. Okay, thanks. Yeah, I think it may have become 8 now. I don't know. 4 is what I'm used to. Okay, so we'll just say 4. Okay. Thank you, Kyle. So my n is stored in memory at some 4 consecutive bytes. Okay, there's 4 consecutive bytes in memory. Let's say that is 4A3E62. Right? It's a memory address. That's a memory address in hexadecimal. So that's all right. And what's the memory address of the next byte here? 4A3E63. Yeah, this is consecutive memory location. So it's 4 bytes, and they're there. Now, this is a memory address, and how big are memory addresses in C++? In most current architectures, how big are addresses? I believe addresses are 8 bytes in length, right? Because if you have 32 gigabytes of RAM, you can't address any random location because it's 32 billion, right? Because in 4 bytes, the maximum number you can represent is, I don't know, 2 to the 32 is 4 billion, right? Even if it's unsigned, it's 4 billion. So if you have that much memory and you want to address the individual bytes, you need to have a pointer that is also capable of holding big numbers. So I think a pointer is 8 bytes, and you can find out, right? So you can do a quick experiment and say, C out size of star n, address of n, size of a pointer, and it'll tell you exactly how big a pointer is in your architecture, right? So, but anyway, forget that. So n, let's say n is the value 10. N equals, pick something that's easier to represent in binary. All right, 10. Okay, so 10 in binary is going to be 0, 0, 0, 0, 0. No, 1, 0, 1, 0. Right? 1, 0, 1, 0. 8 plus 2. Okay, so that's the value 10, and of course, it's an integer. If it's an integer, how is it going to be represented? In 4 bytes. So my n in 4 bytes is basically going to be, also there's a thing about big endian and little endian. Do you guys know about big endian and little endian architectures? This is timer. This is when I'm supposed to start talking to you about this topic. Okay, right? You guys know about big endian and little endian? Do you know what the story is behind that? Big endian and little endian? Right. So how many of you have read Gulliver's Travels? Gulliver's Travels? So do you know about big endians and little endians? A long time ago? Okay. All right. There was a Brobdingnanigans or something like that. Yeah, a long time ago for me too. Right? So Gulliver goes to a country of giants. And then he goes to Lilliput, a country of little people, right? It's a fantasy. It's a satire, actually, based on. It was a satire. I think it was Jonathan Swift in England, in ancient England, right? Not ancient, but he wrote this as a satire of aristocracy and of Britain during his days, where people had classes and saying, and there's warfare happening between two different clans who pretty much are, have the same kind of ideals. It's not like one where one believed something and the other, well, yeah, maybe they actually did it. They're both humans, or they're both people, or creatures. Anyway, so Brobdingnagians, there are these two countries. They're fighting with each other. They're at each other's throats because they have an ideological difference, right? One country believes something and the other, that's the only difference between the two. And what is this ideological difference? The one country believes that eggs should only be cracked on the big end, okay? You shouldn't crack it on the small end. And the other country believes that eggs should only be cracked on the little end. Okay? So they hold on so hard and fast to these beliefs that if you defy it, it's a sacrilege. You're immediately an infidel, all right? You need to be destroyed. So they are fighting with each other just because they disagree on this fact, which is, ultimately doesn't really matter if you think about it, right? So, and Swift intended this to be a satire on British society, but it's an interesting story in its own right. So, to the point that, in computer science, we adopted one of the interesting things that Swift came up with. Right? So if you take an integer like n, we're going all the way back to lecture 1 on day 1. Look at how beautiful it is. Right? You start talking about data representation, and then talking about pointers. We're referring back to stuff that we learned in the first lecture. All right. So n is that number here, and it's but n is an integer, so it needs to be in 4 bytes. 4 bytes, right? So if it's in 4 bytes, think about it, right? So think about it. So you have to now refresh all. Now, because it's in 4 bytes, I'm going to call these the 4 bytes of n, right? That's n, let's call it n of 1, n of 2, n of 3, n of 4, right? So let's say that's n sub 1, n sub 2, n sub 3, n sub 4, okay? So those are the 4 bytes of n. Now, this is the value of n. That's the value of n. Now, can someone fill in these 4 bytes for me so that together this 4-digit in a 4-byte number, that 4-byte number together as a binary number should give me the value 10, right? The quantity 10 should be computed by that binary number. So what should be the values of the bytes in these 4 bytes? What are the values? Can someone tell me that? GDA?
0 everywhere except the last digit, 8.
0 all the way. So this is going to be 0, 0, 0, 0, 0, 0, 0, 0, right?
Oh, in binary, I was going hexadecimal.
Yeah. I know, I understood that. That's why I was translating what you said into binary. Okay, so DDA is saying 0, 0, 0, 0, 0, 0, 0, 0. That's also 0. Okay, and the last one is going to be 0, 0, 0, 0. 1, 0, 1, 0. Now, do you think that's a reasonable representation of the number, the value? Which means that these 4 bytes are going to occupy these 4 memory locations. Or just stay in step with me all the way through, right? Because these are going to be tiny steps, easy to understand one from the next, one from the previous one, but right? So those 4 bytes are going to occupy these 4 memory locations. Are we okay with that? Okay, now here's the thing, right? Now, when we talked about decimal numbers, we were saying, here's this very interesting oddity, which most people don't even pause to think about it, but it's an oddity, right? Because in English, which is a language we use most of the time here in class, words are written from left to right. Did we talk about this before in class? The ordering? Left to right, right to left? No? We did?
Arabic languages.
Yeah. In Arabic languages, it's the other way around, right? So if I were to write a number in English, the text would be, this is a number. This is a number from left to right. But the number I write, let's say it's 527 or something like that. I write it as 527. But that's not the intuitive way of thinking about the number, right? Because increasing powers of 10 are going to the left. As the number gets bigger and bigger, it's growing on the left, not on the right. The increasing powers of 10 are going on the left, not on the right. Right? Does it make sense? Because if you think about the English way of writing the numbers, or the Indo-European way of writing numbers, this should probably be written as 725, right? Because the 7 ones, that's not enough. The ones are not enough, so I need 2 10s on top of that, and then, whatever, 500s. So that's, and the reason that happened was because, originally it was like this, but then, the way that we got the number system today was, taken from there by the Arabs, and then brought by the Arabs to the West. And so in the process, the ordering got changed. And today we don't even realize the ordering got changed. We're perfectly comfortable, right? We can do arithmetic with big numbers without having to mess around in our heads thinking, oh, I got to do this. So, but the reason I'm bringing it up is because there are 2 valid representations of numbers. 2 perfectly valid, and the only reason we think that what we are working with today is valid is because that's what we've been used to. On the other hand, if the number system, was didn't go through that inversion process, we would be using the other kind and say that's the normal thing to do. Okay, so from that, but the thing is, when computer scientists came up with chips and architectures, they had the luxury of starting not from existing history and biases, right? Saying, oh, you got to do this particular. So what happened was it kind of bifurcated into two major, families of computer people, as it were, right? One family said, here's how I'm going to store a number. I'm going to store the number in this way, right? So I'm going to store these 2 bytes before those 2 bytes. So in other words, if I have a 4-byte number, I would say, N4, N3, N2, N1. I don't know if the exact order is right. Maybe it's N3, N4, N1, N2. I got to look it up. But it's possible to store it in this way, yes? Because you just interpret the bytes differently. So this is called the least significant byte in the number, right? Just like if you write this, decimal number, this is the least significant digit, right? This is the most significant digit. Why? Because if you change the least significant digit, you get the least amount of change. But if you change the most significant digit, you get a big change in number. Yeah? So if 7 goes to 8, I increase by 100. But 5 goes to 6, I increase by 1. So this is the least significant and the most significant. Now this is base 10, decimal, right? But now consider this number here. That's a 4-byte number. And 4 bytes are N1, N2, N3, N4. Those are the 4 bytes. Now in our data representation class in the first week, we saw that even though it's a 4-byte number, what are the total number of different patterns, different bit patterns that each of those bytes themselves could have? How many different numbers can just N1 represent? Forget about the remaining bytes. Each byte, how many different shapes can each byte take? How many different bit patterns can you hold in each byte? 256, right? Include 0.
Oh, is it 0?
Yeah. Zero is a pattern. It's a valid pattern, right? So in digits from 0 to 9, he includes 0. So 256 different patterns. So think about it, and I think it's in the first data representation quiz. Can you not think about that byte as a digit, 1 digit, in base 256? Right? So that's basically a number. It's a 4-digit number. So N1, N2, N3, N4 is basically a 4-digit number in base 256. And you can verify that too, right? Because you can just calculate this on a piece of paper using a calculator. You'll find it's exactly the same, right? So N1, N2, N3, N4 is simply equal to N4 times 256 to the 0. That's basically units, right? This is 1 plus N3 times 256 to the 1. Yeah? Can you do that? And you get exactly the same number as if you calculated this using binary. You'll get exactly the same value. Now, but all of this is predicated on the fact that these bytes have a particular position in the string. Because I'm indexing by position. I'm saying that's the first byte, that's the last byte. Now I could just as well have built an entire family of computers, which is world famous, everybody's using those computers, in which the ordering was totally awkward. Maybe I had an ordering for all of my 4-byte integers that went N2, N4, N1, N3, right? Some totally weird ordering that only I know. And maybe I'm a computer manufacturer that came up with that particular ordering without publicizing it. It's stupid because it's easy to find out. But just to make it hard for other people to integrate with me, right? Anytime you do some weird shit in your programming, that really is a signal saying nobody touched my code, right? Because I'm going to make my code hard for you to understand for a reason, because I don't want anyone fiddling with my code. It's my code, don't change anything in it. So you have that kind of possessive mindset about your code, you're going to make it hard to read. And and you'll be unlucky actually. Nobody will in fact fuck with your code. You'll be perfectly safe with your code, nobody's going to touch it, and then when you die, your program dies with you. Right? Most programs follow that path. But on the other hand, you can make your code easy to read and friendly, and people will try and maintain it. It'll live long after you're gone too, right? So maybe if I came up with that really weird ordering of bytes, then I would be able to understand that, but other people won't be able to. They have to resort to complex logic to decipher the number that I put in those 4 bytes. but it so happened that I think it was Motorola and Intel. Now, I might be wrong, you got to look it up, right? Motorola decided that their bytes, the integers, actually there were only 2 bytes for integers at that time, not 4 bytes, 2 bytes for integers. They said our integers are going to be BA, A and B, N1, N2, right? We're going to store all our integers on hardware as N2, N1, right? And Intel said, we're going to store all our integers as N1, N2, right? Now, I don't know exactly, there's some mismatch. I mean, DDA, who's a hardware guy, can correct me here, or you can post in the forums if you have time, right, to fix that. But there's this ordering difference. So if you took a program, an integer that's been stored on a Motorola machine and took it to an Intel architecture, it wouldn't work because the numbers would be computed differently, right? So they're not intercompatible. So the difference, therefore, so it's when you're in higher level language, higher level languages like C++ and Java and C and so on and so forth, you don't actually get to specify. I want an integer and it should be stored as N1, N2, N3, N4, right? You just say I want an integer, right? That's all you say. And so the compiler has to decide, because the compiler knows what architecture it's compiling to. The compiler knows this C++ program needs to be compiled into Motorola code, or this C++ program needs to be compiled into Intel code or ARM code. Right? The compiler knows which ordering of integers you should put. So if you look in the compiler code, and also, you see this a lot in data communication software, even high-level languages, right? Because in data communication software, you got to send some information from my Mac to another computer somewhere else and make a connection. And maybe my Mac is based on an Intel chip. I'm sending it to an ARM machine somewhere else, right? Some other architecture. So that machine interprets numbers as N1, N2, N3, N4, whereas I'm sending numbers as N4, N3, N2, N1. So I need to be aware of the format in which the receiver is getting my numbers. So all of this becomes useful now when you start coding for communicating between processes, between machines. So I think one of them, Motorola, the way of storing numbers as N2, N1 instead of N1, N2 became called as little endian, right? Because it's the same act, it's the same number, but Motorola said, we'll look at the number from this side. So for them, all the numbers were N2, N1, N2, N1. The second byte goes before the first byte. So the most significant byte is on the left, right? Just like our decimal numbers maybe, right? Whereas for Intel, it was the other way around. And so it's little endian and big endian. So that's the history between little endian and big endian, right? So you'll see this in code. When you're writing when you're writing code that you need to work with individual numbers, quantitative values, then it becomes significant, right? Especially when you're communicating from one machine to another. All right, so there are these 4 bytes, and these 4 bytes have to go there. So let's assume that we're just little endian for now, right? Well, one of those endians, I don't know what, right? So that would be 0, right? That'd be 0, that'd be 0, and this would be 1, 0, 1, 0. What is it? No, 0, 0, 0, 0, 1, 0, 1, 0. Okay, so that would be my number. That would be M. In my in my system, in my program. However, that's the value of n. Now, because n is 10. Now suppose I don't want the value of n, but I want the place where n is stored. Where is n stored in memory? Because I want to go to where the n is stored and change it myself. I don't want the compiler to change it. I want to change it at runtime. I want to know where is n stored. So what is the answer to that question? Where is n stored?
Use a pointer.
What is that pointer? What is the value of the pointer?
Pointing at the value of the return address of n.
No. What is the value of n? What is the value of the pointer in this case?
The value of the pointer in this case is star n, or the reference to where n is, like n.
Right, but I gave you that number. I gave you that number, right? I gave you the address of n. What is the address of n? Come on. You guys are not even listening to me?
Is this is that for the n on top, like the one with the 5?
Yeah, so my n is being stored in memory, okay? The value of n is being stored in memory in these 4 bytes. Okay, so there you go. That's my n, 0, 0, 0, and then the 10. Yeah, that's my number. Now, what is the value of the address of n? Not n itself, but the address of n. Where is n stored? Right? What is the value of
I
that?
think it's n plus 3, and then just n plus 3.
No, not n plus 3. But I want to know exactly what the value is. Where is my room number? Where, my room number as a person, right? So where is n stored in memory? I gave you that value. I wrote it on the board. Okay, so this is it, isn't it? 4A3E62. All right? That's the memory address where n is stored.
Yeah, I could.
You could see it, of course. Yeah. Right, fair enough. Right? So this is the memory address. And so if I say I want the address of n, not the value of n, then I get this number here, 4A3, right? So now let's say I have another variable. So I have int star p, okay, equals address of n. Okay, this is the syntax. Now, and this syntax means, so star is called a dereference pointer. Dereference means a dereference operator, right? It means that what follows a star is a pointer. Don't give me the value of the contents of the pointer, but tell me what the pointer itself is. Right? So star, no, sorry. This means don't give me the value of the pointer itself, but tell me the contents of what it has. That's what the star means. This is dereference, right? So in star p means p is a pointer. Go to the address of p, extract the contents from where, that address, and give me the value. So star means contents of. Read star as contents of. Star has two meanings in C++, right? It actually has three meanings in C++, right? After this forward slash, it starts a comment, a block comment, and then inline as an arithmetic operator is a times, right? As a unary operator, it is a dereference. I think it's the only operator in C++ that has three functions. No, I think there's some other operators. Okay, so this is the dereference mode of functioning of the star operator. So this means take the contents off. So if n, so now in this case, star n or p, right? Let's say p. What is the value of p? Suppose I did this. What is the value of p? After that statement has been executed, int star p equals address of n. So the ampersand basically means not the value of n, but the value of its room number, the address. Okay, ampersand means address of in memory. Okay, so what is the value of p after that statement has been executed?
It's that 4A, it's the memory.
Exactly. Thank you, Christopher. Okay, so after that statement has been executed, p will be equal to 0x 4A. What is that? 3E62. Does that make sense? So the address of n, yeah.
Well, how can the A's and E's be an integer?
Oh, it's a hexadecimal number.
Hexadecimal.
Right, so I got the 0x in front.
Yeah.
0x means that number is hexadecimal. There's, I think 0b means it's binary. You can give 0b, 10, 10. Yeah, I think so. All right, so that's p. That's the pointer p. And now if I want the contents of p, I'd say int m equals contents of p. Yeah, that's how you read it. Contents of p. Now what is the value of m? What's the value of m there? Come on. Run the statement in your head, right? I did int p equals address of n, and then m equals contents of p, right? So what is the value of m after that statement has been executed?
It'll be the return address of p, which is the 0x4q362.
No, try again. All right, so well, maybe, I'm saying this gets executed after this, okay? After that. So I'm going to assign, not here. So int star p equals address of n, and then m equals star p. So what is the value of m after that statement has been executed? Someone other than Christopher, GDA, someone, or Jason, someone take a crack at this question, right? Tell me, what is the value of n or m after this statement? Come on, I know it's the last class and all. Yeah, sorry, Max?
The address of n.
Okay, so Max says is the address of n. I think that's what Christopher said too. No, take another crack at it, okay? So remember what I said, star is a dereference operator, okay? Yes, Ida.
I think is
The value of n, what is it?
10.
10, thank you, okay? So at this point, n will be 10. Yeah? Because P is pointing to the address of n it has the value 10, okay? And m is simply the contents of whatever P is pointing to. Now P is pointing to n, so what are the contents of the memory location P is pointing to? It's 10, because P is pointing to the same place that n is. Does that all make sense? It's important to be completely comfortable with this before you go on to manipulating lists, right? Because there is no better way to shoot yourself in the foot and get lost in a tangle. It really is a tangle, right? So a tangle of pointer strings, right? So in your lab, in your linked list, you got nodes that are connected, like beads in a necklace. But if you are not 100% comfortable with connecting these nodes together, you know how it is, when you try to string up, or you're trying to untangle a bunch of yarn, things like spaghetti, right? People talk about spaghetti code. That's nothing at all compared to spaghetti pointer links. So if you have spaghetti pointer links, you're totally stuck, because at least code you can see, right? In code you can see, but if you're manipulating a graph, and the graph has nodes that go everywhere, the only way you can tackle that is algorithmically. Most of the time, right? And even with algorithms, you got to work it out, on small graphs first and make sure it works. All right, so it works. So let's try a bigger graph. Is a greedy approach works, or is there better? All those things you learn in C2C. But tangly, messy pointers, that's the last place you ever want to be in. Whether it's Java or C++, Python, doesn't matter, because it's now you're dealing with a virtual structure. You're dealing with something that you can't see. Right? All through 2A, everything you did, you could see, right? You see the code, you can fix it, it's an error, you can run through a debugger. But debugging with pointer code is really hard if you don't know what you're doing. If you know what you're doing, it's fine, right? Because you can say, I need to look at this memory location. But sometimes what happens is that, you want to reset pointers, and you want to say, well, I got the structure and this node, this complex structure, this particular node, this pointer, this link needs to point here instead of there. And you go in and change that one link, right? And then something else doesn't work, and you need to go into that forest again and find out if that link is still pointing where you set it to, or did it originally point where you wanted it to, right? You can imagine already what a morass of difficulty that would be, yes? Because already, so yeah, when it comes to pointers, here's my suggestion, right? Before you get into, deep pointer manipulation, just get 100% comfortable with what pointers are. It doesn't matter if it takes a lot of time, but just keep working through examples and get completely comfortable with what a pointer is just an address. Once you know that it's just an address, then you can manipulate it right. So we'll see an example when we manipulate lists. Okay, so that is basically what a pointer is, and so a C-style string. In C++, you have strings. This is another topic that is in the syllabus. Strings in C++, they're not just arrays of characters, right? In C, we saw that strings were basically just arrays of characters, one-dimensional arrays of characters in C. But in C++, a string is an object that has things inside of it. So it also has the array of characters, but it has other things. The length is stored, is not calculated at runtime. In real time, it's stored as a number, and it has other methods attached to it, and some other attributes, static attributes, and so on. So the string is an object. Now, if you want to manipulate a string in C++, you can call the string methods to say, okay, go in and change that string in this way. Even though strings are immutable in C++, like that. But it is also possible, because C++ came from C, to tell the compiler, no, forget about manipulating the string for me. Just give me the character array inside the string. Just give it to me, and I'll take care of manipulating the string myself. So getting the character array out of the string. Then once you get the character array out of the string, you can use that to pass it to C-style functions that manipulate strings, right? Now, C-style string manipulation functions are really thin, right? Because they were, written for the days when we didn't have a string class. You had to go in and manipulate individual bytes. But as a result, they're very thin and efficient, really fast. If you want to manipulate strings, I don't think the only way you can get them to be faster than you can manipulate strings in C is to do it in assembler, right? Because in assembler, you know exactly what the algorithm is and what you're doing, right? But the C routines for manipulating strings are already as efficient as that. You can't get I don't think you can get faster than that, other than a faster architecture, right? So where were we going with that? Yeah, see, strings. So if I have a string, S equals string, let's say LOL, right? Okay, so suppose I have that string. Now S is a complex object. I don't have that array of, so I can get that array. All I need to do is say s.c_str. This is a hack, all right? And you can tell immediately by looking at the function that it was introduced by C++ programmers who also wanted to grab the C-style string for some purposes. So they obviously felt that there were some situations in which the native, the native string was more appropriate than the C++ string. Yeah, you can think of situations like that quite easily as you get more experience in programming. But so you can get at the actual bytes by using that. When you get at the actual bytes, you can make character arrays, pull character arrays out of strings, and hopefully you won't have to do any of that, right? In very rare situations, when you need to get the actual character array. Basically, the only time you have to do that, or I've had to do that, is when I have a C-style string and I need to invoke a C function on it, right? So if I have an old style C function, which is written for character arrays, and I want to apply that to C++ strings, and it so happened that the C++ designers had not thought that function to be common enough or popular enough to incorporate into the string library, then I have to use that function, right? Instead of writing my own. Then I have to invoke the cd_str, get the string, and do it on the string. So otherwise, you don't have to do that. So don't waste it. Just imagine, just know that it's possible to get the raw string out of a C++ string by calling that function. Yeah. Okay. So that's a C-style string. This is a pointer. Now let's take a look at more complex objects. And I'll also cut code here in class. Unfortunately, that clock is not working. But I'll create some code. I'm coding on the whiteboard just because I haven't opened up my laptop and the projector takes a little while to warm up. But I will code in a short while. Okay. So that you can see how these things are actually used inside of an IDE. All right. Now let's take an object. How do you create? This is one topic I didn't cover. So your pointers, I showed you how to get the address of existing variables. So you have an integer, you say address of the integer, you get a pointer. Yeah? Now, there's a couple of interesting things about pointers, right? So suppose I have an array of numbers, okay? Suppose I have an array of numbers, and each of these is 4 bytes, right? It's 4 bytes. 4 bytes. It's an array of pointers. So int, say arr int. Okay. Okay, so that's my array of numbers. Now, in C and C++, if I have a variable that points to the beginning of the array, you can only point to the beginning of an array using a pointer. So I would say int star np, right? A number pointer or something like that equals that. That it might be a memory address, 0x3e4a2, right? So my pointer is set to the beginning of the array. So this is the first number. It's the address of the first number in the sequence of numbers I have. They're all in contiguous locations. Now here's the interesting thing about C++ pointers, right? And pointers in general in C and C++. If I increment a number, what do you normally expect to happen? When I increment a number, what do you normally expect to happen? Suppose I have a number and its value is 5, right? And I say n++, right? N is 5, and I say n++. What is the value of n? 6, right? Okay. Now suppose n is it's not an integer like n, not a float. It is actually a pointer. Let's assume it's a pointer to an integer, not an integer. Okay, so pointer to an integer. So np. right? This is not an integer, it's a pointer. Now what happens if I do np plus plus? Np is pointing to this integer, right? What happens if I do np plus plus? Remember, each integer is 4 bytes long, right? And I have and p is a pointer that points to the first byte. There's no address for 4 bytes, right? You don't have an address for 4 bytes because each byte has a separate address. So I can't have a single address that says this address is 4 bytes. No, that doesn't make sense, right? So p, even though I'm pointing to an integer, doesn't point to the 4 bytes. It only points to the first byte. And after that, it's left to the system to know whether it's big endian or little endian to interpret the 4 bytes starting there. Right? So it's only pointing to the first byte. And so my number n is stored at 3E4A2, 3E4A3, 3E4A4, 4, 5, right? 3E4A. So these are the 4 bytes in which my number is stored. But p, the value np, right, is what is the value? That value is this guy here, the first number, not the 4. This doesn't make any sense, right? To give 4. So the value of p is this number. Okay. Now what happens if I do np plus plus? Right? Not np. Let's just say p. Right. Right. The value of my pointer is the first number. That one. Okay. So what happens if I do p plus plus? What is the value of p plus plus? Right. When I increment p. Right, or p equals p plus 1. What do I get? I told you what the value is before I increment it, right? Before I incremented it, it's 3E4A5, right? Not 9, okay? 3E4A5 is the value of the pointer to an integer before I incremented the pointer. Now I did a plus plus, so the pointer's been incremented. What is the value now? Can someone tell me that? Take a guess. You don't have to. So when I say, can someone tell me that, you don't have to tell me the right answer, right? You just have to tell me some guess, right? What do you think? What do you think happens, right? So here's the thing. In all my classes, okay, not just 2A or 1A or cloud, doesn't matter. In when there's a question, when there's an open question, and I say what happens, I hope really that you're not searching your memory banks or looking up information to say what is the right answer to that. What is the answer in the textbook, or what do the modules say, or what do all these great people say, right? What does the documentation say? That is the wrong answer to me, right? I don't care if you tell me the right answer, but it's not your answer. If it's not your answer, it doesn't help me, it doesn't help you. Yeah? So, like I said, 10 years from now, if someone says, why do you structure your for loops or while loops in this particular way for this program, and you say, oh, that's how Anand taught us to do it in CS2A 10 years ago, right? That would be the stupidest possible answer anyone can give, right? So if you still remember me in 10 years, that would be a loss, right? But if you don't remember what I said in 10 years, that is also your loss. So remember what I say, but the only way you can make it your own is to detach it from me and say, does it make sense? So when it makes sense, it doesn't make my sense. Whose sense does it make?
Your own.
Your own. So when it makes sense, it is now attached to your sense, not to my sense. When it's attached to your sense, it's going to be there as long as you have your senses. Does that make sense? Okay? So everything I say, if it doesn't attach to your sense, it's gone. Toss it out the window. Right? Or ask me. You can ask me, hey, you said something, it doesn't make sense. Right? And I'll say, well, it doesn't make sense for you, it makes sense for me. Why is that so? Is your sense different from my sense? No, it can't be. Everybody has the same kind of sense, everybody has, we all know what is possible in general, what's not. We don't have, assuming that we rule out people that have blind faith, right? So I can see what's going on, so then I can say, all right, so this way it'll make sense to you too, right? And then that's the way I can remove myself from your homes. By your homes, I mean your senses, right? Until then, I'm beholden to you. I have to live within each one of you and say, this is the right thing to do, this is the right thing to do. You can only let me go and make me free by saying, I don't need you anymore. You can go and enjoy your life. I can take care of myself. That's the best gift you can give your parents, right? Yes? Okay, so that's the best gift you can give your teachers too. Yes, Max?
I was gonna make a guess because it doesn't sound like you incremented that number by 1.
Yeah, okay, good, thank you, Max. Okay, so it doesn't make sense, right? So what is it? Because if I say, you know, and P++ is going to be 3E4A6, it doesn't make sense at all. What am I going to do with, suppose I had that, suppose, you know, C++ gave me that feature. It said when you increment a pointer, it goes up by 1 byte. You know, that's what you expect it to do. So, yeah, I'd say, yeah, that's fine. But then my programs will all of a sudden become a whole lot more complicated. Because every time I have a pointer, I need to know the size of that pointer, because if I want to increment the pointer, I can't increment by 1, I gotta increment by 4 each time to go to the next pointer. Yes? So because that is the most common use case, the designers of C++ said, when you increment a pointer, we're not going to increment by 1, we'll increment by the size of the pointer. You don't have to remember the size of the object. Yeah, how beautiful is that? See, it's just a simple decision, right? It's a simple decision. Designers of C++ could have chosen to say that when you increment a pointer, it goes up by 1. So you better, you know, always be mindful of how big the object is the pointer is pointing to, so that when you increment a pointer, you can have a special function that says, you know, increment by the size of the pointer, size of the object, not by 1. But it is something that is routine and, more importantly, can be mechanized, right? So that's important. If it can be mechanized, meaning it can be done without human input, then the computer should do it, right? If it requires human input, then it's okay, you know, we gotta go in and do all that shit. But if it does not require human input, then the computer should do it. Don't care about people that say, no, the computer should only do what it's supposed to do, because if it starts doing everything, slowly it'll take over everything that humans do, right? And then humans won't have anything left to do. That's the stupidest thing that anyone could say, right? Because, you know, they're doing it all day long. When they pull up their phones and talk to their friends, why don't they just, you know, walk over to where their friends are, you know, catch a plane and go to New York and talk to them? They pull out their phones and talk. They do that because, you know, technology makes that possible for them. They don't complain about technology then, right? You're gonna say, you know, they're gonna say, oh, technology took away the time I could have spent in a plane, red eye to New York, right? Oh, all the time was gone because of this blasted technology. They don't say that. So, you know, if something can be computed mindlessly, then your mind is too precious a resource. That's what I'm saying. Yeah? Your mind is a precious resource. Don't waste it on mindless tasks. Right? Mindless tasks should be done by mindless automata, by robots. You know, mindful tasks should be done by humans. So, and so the C++ designer said, you know, this is mindless. You know, every time you want to increment a pointer, you're going to do this, and what's more, the size of the object is known to the compiler. The compiler knows the size of the object. So why doesn't the compiler do it for you instead of you doing it every time? So there you go. One piece of routine grudge work has been removed from your, you know, your perspective altogether, because the compiler did. So that's why in C++, when you increment a pointer, it increments by the number of bytes that a pointer points to, the object. So you know, how cool is that? So you can have an array of pets. You can have an array of pets, and your pet object, I don't know, how big is a pet object? You got an ID that's a long, that's, you know, let's say it's 4 bytes for a long, or 8 bytes for a long. You got a name, a string, and a string is an object. So an object is probably stored as, let's assume it's stored as a pointer. No. Let's say a string object is 24 bytes, right? It has a pointer inside of it and some other. So let's say 24. So 8 plus 24, that's 32. What else does it have? It has a number of limbs, right? It has a number of limbs. That's another 8 bytes. No, it's a short integer, 4 bytes. So it's 32 plus 4, 36. Okay. So let's assume a pet object is 36 bytes long, right? So 36 bytes. Then so this is my pet object, right? This is my pet object, and it has an int ID. That's 4 bytes. Oh, actually, it's long, right? Long, and it's 8 bytes. String, 36 bytes. Name, right? Name, 36 bytes, and then, you know, number of lumps. I don't know, integer, 4 bytes. Okay. So my pet object is actually a 36 byte thing, not a 4 byte integer. 36 bytes. So I can have an array of pet objects. So it's my pet 1. Pet 0, right? Pet 1, and so on. So each one of those is 36 bytes now, right? So if I say, you know, P equals, let's say, address of pet of 0, right? It's the same as saying p equals pets. They're the same, right? So assigning an array is the same as assigning the address of the first element of the array. Yeah? I mean, this is all, okay? Are you guys following? Because if I lost you and I'm just going on ahead, it's no use, right? So if I've lost you, you just have to raise your hand and let me know, right? And if I go off on a tangent, just pull me in, right? Keep doing that. Thank you for doing that. Okay. So I got an array of pets, and I get p is the address of the first pointer. Now if I do p plus plus, p will get incremented by 36 bytes, not by 1 byte. Yeah. So that is an important piece of information to keep in mind as you're programming with pointers. Okay. All right. So that's pointer arithmetic, by the way. Okay. Increment and decrement of pointer will move the pointer by the size of the object, not by 1 each time. So just keep that in mind. Okay. And finally, the only other thing that we need to talk about before we start implementing some code. We got time? We got time. All right. Is link structure manipulation, right? And something that you will face in your last request is how do you suppose I have a linked list, okay? A linked list in which I have a bunch of information and also a pointer that points to the next node. All right? Also a bunch of information, and this has a pointer that points to the next node. Okay? And then that one points to nothing, right? That's a null pointer. The last element is null, and each element points to the next element. So that's your point. Now let's say I have a brand new node, okay? Node that I need to insert. I need to insert in this location. Let's say this needs to go here, okay? Let's call this P. That node is P. That node is Q, right? And let's call this R, okay? So 3 nodes. There's a node P, there's a node Q, and there is a node R that I need to insert. It's a brand new node that I've created. It's not part of the linked list yet. It's not in the chain. It's a bead. I've got this bead. I need to string it in. And I know the specific place where it needs to go. It needs to go after the P, before the Q. That's where I need to put it. How do I do that? Okay? So it's a very common, I think it's an idiom, right? It's an idiom. It's a very common sequence of steps that are used to make that change. To take this new value and slot it in there. And once you've done it 2 or 3 times, then you know, right? 2 or 3 times, then you know. Anytime you need to insert something or manipulate linked lists, you can picture it instantly in your head. This is exactly what's going on, right? So how do I do this? So you know that R also has a null pointer. You just created R, this brand new node. Okay? So R also has a pointer, a next pointer, right? Okay, next pointer. So as soon as you create the node, you call the constructor for the node. Where is R pointing to? Where is the next node of R pointing to? Now R has some value, right? It has a data value. Maybe the name of the pad is Fred Flintstones, number of limbs, all that is set, and it also has a next pointer. The next pointer, I don't know, where does it point to? Before slotting it into the list, right? I just call the constructor on the node. He's given me a node with the data filled in. The next pointer is not pointing anywhere, right? So where is it pointing to? For a brand new node which has not been slotted into the big list, the next pointer is pointing to null. In the constructor, you just set it to some random junk value, right? It could be junk or point to null. It's better to point it to null. So brand new node, which hasn't been slotted into my list, has a null next pointer. Okay, that's where we start. Okay, so we start there, and we need to take that node and fit it here. How do we do that? So always do it on paper. When you do it on paper, you can visualize it, and then you translate it into code as a piece of cake, once you can do it on paper. Okay, so now what I need to do is, remember, here's how you do it without using any temporary variables and all, right? So the first thing I do is I'm gonna leave my original list untouched, not messing with the original list, but I got this new node with a next pointer. I know where its next pointer should eventually point, yes? Where should its next pointer eventually point?
Q.
This should point to Q, right? This should point to Q because it's going to go before Q. So all I'm going to do is take its next pointer and make that point to Q. right? Now I haven't touched the big list at all. Right? At any point, if I lose this, no loss. Because, you know, the original list is just there. Untouched, okay? So this pointer is gone. Okay. Everybody okay? Now all I need to do is take that link here, okay? Break that link and make that point to R. Okay? So I'm going to take that link and I'm going to break it. Okay? I'm going to take that and point to R. Okay? How many steps? How many steps did you know, how many statements would that be? How many steps are involved in making that change? Now, do you agree now that Q has been slotted into the right place in the list? Or yes or no? Yes or no? Is Q in the right place? Because, you know, Q, R, right? R, right? So P points to R points to Q. So everything is in place. And the sequence of steps to do this is equally straightforward, right? So what I have to do is, let's say, you know, R equals new node, you know, data. Say data, comma, node. Okay? So it gives me a brand new node. It gives me this guy here. But it's not being connected to anything. It's just, you know, it's like you get these Arduino chips, and you know the chips are, you have to connect them, right? So it gave me this chip, this block here. That's my first step. The second step is I'm going to take this guy's next pointer and point it to Q. Okay? So I'm going to say, let's say I want to insert after P. So this is called insert after, and then I get past P as a parameter. Okay? But of course, this is not what you'll do in your quest, right? In your quest, you'll have insert after a current location or something like that. Right? So you should be able to generalize from this. Right? So I got this. Now I'm going to say R arrow next equals what? I want to insert R after P, right? So what do I want R's next to point to? Go on, be bold, right? Say things. It's better to be wrong. I always say it is better to be wrong, than not to have an answer at all. I was telling my cloud students yesterday that, you know, I usually see this in my 2A, the first year students. They're always so shy about being wrong. Always shy about speaking up because they think other people will know the answer, and they're all, you know, I don't want to speak up and show how much I don't know. That attitude is really bad, right? Point to Q. Thank you. All right. So R arrow next equals Q, right? But what is Q? Where do I have the value of Q? No, I don't have Q. Q then, yeah. Sorry?
Q is just pointing to null right now.
Q is not pointing to null. Q is null, right?
No.
No, not here. So I'm sorry. We're talking about this here. Okay. Inside after P. No, I wanted to point to what would be Q, right? But I don't have that. That's not being passed to me. What is passed to me? I only get past P, which is insert the node after here. So what should R's next be? R's next is nothing but P's next, right? P is pointing to Q. So even though Q has not been given to me, I can get the value of Q by doing P arrow next. Yes? So R's next is nothing but P's next. Does everybody agree? Because these two statements will look very confusing. I can tell you, it looked very confusing to me the very first time I encountered that, right? Because it looks like circular assignment, but it's not, right? So R's next points to P's next. And now, all you need to do is, you know, you've done this. You want to have P's next point to R. Yeah? Now you can say P next. You're done. Yeah?
So what you're trying to do is get R's next to point to R through P's next. Is that what you're trying to do?
No, I'm getting R's next
Yeah.
to point to what B was pointing to next.
Okay.
And then I'm going to take P's next and point it to R.
So R's next is pointing to P, and then P's next is pointing
No.
to
R's
R.
next is pointing to P's next.
So R's next is pointing to the value at P's next,
That's Q.
which is Q.
R's next points to Q.
Yeah.
And then B's next points to R.
P's next is pointing to R. Okay. That
So
makes sense.
now, Jessica, welcome. All right. So do you see how this chain has now been formed just using these two lines, right? Ignore this line. This is a constructor, right? And it's a constructor for the node. Maybe you get past the node, but these two lines are the core of inserting an element into a list. Yeah. Okay, so that's how we, and by the way, yeah, there's one thing I forgot to mention when we were talking about pointers, is that, I said that you can get a pointer by using the address of operator. Okay, so you say address of n, and it gives you a pointer to n, right? But you can also get a pointer another way, which is in fact the most common way of getting pointers, is telling the operating system to give you some memory on the heap, right? So you have the stack space and you have the heap space. We talked about that before. Right? When you say to the system, I want like a gigabyte of RAM to store some, media file I downloaded, or something, or even I want 4 bytes to store an integer. So you can tell the operating system, give me that memory on the heap, not on the stack. Right? On the stack, you just say int n. But if you want the memory allocated on the heap, and say, give me 4 bytes for storing an integer, then what the operating system will do is allocate the 4 bytes and give you a pointer. It won't give you the actual values, it'll give you a pointer. So there, you use what is called a new operator, okay? As a new operator. And the reason you gotta be really careful when talking about new operators, the new operator, is that it does allocation of memory on the heap, and you gotta be super duper careful in bookkeeping, right? You gotta be like super careful when you use new to make sure that everything you allocate memory for, you also deallocate before your program dies, right? And actually, it's not before your program dies, because when your program dies, the operating system automatically cleans up all your shit for you, right? It'll make sure that anything you allocated and did deallocate gets released into the pool. So, but it's bad programming practice to rely on the operating system to do that for you. That's why I say, people come and say, should I learn C++ or Java as my second language, right? So I think the first language to learn is good to learn an untyped language, because like JavaScript or Python. PHP, so not untyped, weakly typed language, so that you're not intimidated or scared away by saying, there's got to be an integer, it's a double, and I don't know what a double is, and a float, and all those things really scare away beginning programmers. So initially you just want to know. I want to throw things together and see if it works, without having to know about bytes and bits and so on. So I think JavaScript, Python, scripting languages are good because they're not strongly typed. And people say, what's the second language I should learn, right? And I think the second language you should learn should really be C++. A strongly typed language like that, which doesn't do automatic memory management for you, right? You take Java, Python, JavaScript, they all have garbage collectors built in, right? It's good to programming those languages. Once you get to a certain stage, there's just things you can do in those languages which are more appropriate, especially JavaScript, right? But I think it's not good to start coding in JavaScript before you get a good sense of how a program works, with memory and so on and so forth. Because what you get in Java is basically a free servant following you around, right? So Java tells you you can be an indisciplined programmer and still do cool things, right? But if you're a disciplined programmer, you'll be able to do even cooler things. Not just you won't be even cooler things, because if you're disciplined, you don't have to worry about a lot of things, right? So like I said before, the greatest thing that prevents people from doing great things is really the worry that maybe I'm wrong, maybe I'm going to crash the system, maybe this is bad for you. Do you think is that a good way to program? Right? Later on, when you have kids, right? Would you like a child who just goes around tossing candy wrappers all over the place, and depending on the parent to come up and clean up after them? No. Yeah. Right? You may be a really rich person, right? You could be a really rich person and have like 1,000 servants in your home who are following you around. But that still is not the right. Don't you feel that's not the right way to grow up, right? Because once you're disciplined, I always feel that the only way to truly appreciate something is to learn the value of not having it, Because when you know what it's like to not have it, then you know the real value, the preciousness of it. It's Shakespeare said that, I think. I was mentioning this yesterday to my college students too. What is that play? I think it's Much Ado About Nothing. I think. Oh, what is it? As You Like It? I get confused. Much Ado About Nothing. Leonardo There's a character, hero, right? And she pretends to die. She pretends to die because, I forget the story, it's a long time ago, right? Because she wants to make her fiance believe that, you know, she's really in love with him or something like that, or vice versa, right? But she doesn't want to pretend that she died, and her father tries to convince her that, you know, pretend you're dead so that he'll really feel your loss, right? So what is he trying to say? You know, he will love you best who feels your loss to sting the most, right? And in C++, you know, learn this, how to do garbage collection and so on, and get bitten in C++, right? By memory leaks. You know, write these big programs that run and get fatter and fatter and immediately explode, right? Saying no more resources, and when I get a segmentation value, die, right? Die many times, die repeatedly, and then in one of those rebirths you'll learn, right? So, oh my gosh, you know, I've been doing stupid things all along, right? So if I do it this way, I won't have to, you know, I won't have to be killed by the operating system. And then, and you realize, and then you go to Java, and you realize that, you know, memory collection, you know, garbage collection happens automatically now, but I don't have to rely on that, but it's a nice thing to have, right? Now, then you turn your garbage collector from being a painkiller into a supplement or a sweet pill, right? Because otherwise, in Java, you'd be dependent on the garbage collector. You can never function at your full potential because you're always afraid is the garbage collector going to kick in or not? If it doesn't kick in, I'm stuffed, right? Whereas if you're programming with a disciplined state of mind in Java, you have a good intuition of when mostly it's going to kick in, right? Because you know, oh, this many objects must have been created and destroyed by this time, and that would cause the garbage collector to kick in, right? So you have these intuitions, you'd be a much better programmer that way. And because you have these intuitions, you have less fear in doing things in Java, because you know your program is not going to die because you're not doing stupid things, right? So you end up doing much better things, and cooler, more powerful things happen, you know, that way. So, so there you go. So that's how we get talking about that in Java and C++. Yeah. Okay. Well, this is how you. I said new, right? New. So when you use new, you get an object on the stack on the heap. Yes, Eric.
I just wanted to remind you the reason you went into that whole thing was because we weren't taking any shots or guesses at why all the processes was going to go that way. And you
All the processing, all the links, the nodes.
Yeah. So you wanted to tell us that story so that we would be more encouraged to try to take guesses.
Thank you. I have a very long story. Thank you. So that's basically. So when you say new, you just get a new object. So get a new object, and that object is on the heap, and you'll get a pointer to it, right? And you can manipulate the pointer just like you do a regular pointer. Okay. So these are the statements. These are the sequence of steps and the corresponding statements that you would use to insert a new node into a list. Okay. And when you delete a node, always, you know, likewise, be mindful, and to hold on to the predecessor, right? And then, hold on to the node that you're going to delete, go to the predecessor, make that node skip over this node and point to the next one, then you can delete this node, okay? Don't delete this node first and then do that, okay? Because you never know what's going to happen. If you delete a node and that node is active, someone might be writing to it, especially in multi-threaded processes, right? So you pull the node out and then delete it. You gotta delete every node you pull out. So here's a good way for you to look at memory management, in a useful way, is to look at your code and make sure that has every new been paired with a corresponding delete. Right? If you can find a corresponding delete for every new, you're good. If not, you got to look over your code more carefully, because maybe you have the same statement freeing multiple nodes. You got to make sure. You got to run the code in your head and make sure, for small cases, right? You obviously can't run it for billions of nodes. For small cases, make sure that you're deleting, freeing up every single node that you allocate. Right? If you don't, then you'll see a program get bigger and bigger. So Yeah, so that's basically how you deal with pointers, dynamic memory allocation, and so forth. Right? Do you have any questions so far? Anything else? Yeah. Do you have a question, Darshan? No. Okay. Yeah, Christopher?
How does the new keyword relate to like list pointers?
Oh, this pointer. You asked me to talk about this pointer.
Yeah.
Okay. Yeah. Okay. So, all right. So, in your methods, in your instance methods, okay, this pointer does not is not relevant to anything other than instance methods, not even static methods. You can have a static method. A static is a global method, right? It's not attached to the object. It's just free floating. But instance methods are attached to objects. Now, what happens when you call an instance method? This is something that's not in the documentation, maybe not in books. What happens is that you may declare an instance method. Let's do a typical one, right? So you say pet class, right? Pet, and let's say it returns count, right? Integer, and count number of limbs, right? Count. Let's say your number of limbs is an array, right? It's an array. Maybe it's just millipedes, right? So and you can have ones and zeros depending on whether a particular limb is there or not. Count limbs, right? Okay, right? And all this is going to do is go into the object, count the number of limbs that particular instance has, and return it. That's all it does. But how does it know? How does it know what to count? It needs a parameter, right? It's a method. Where is the parameter? Where does it get the parameter to? Where does it get the parameter? The object which it's supposed to count the limbs of. It's supposed to. That method is supposed to be invoked on a pet object, right?
Yeah.
Okay. All right. So I call it like this, right? So n equals my pet dot get count limbs, or count limbs, or whatever that is. Of limbs. Now, I'm not passing any pointers. I'm not passing any parameters. It's just an instance method. No parameters. You can understand if I passed a parameter pet here, right? If I passed a parameter pet, this guy could just say pet, right? This guy could say, pet, if pet dot numlimbs equals 0, return -1, right? Else, or return, pad. Okay, so suppose I was passed a pet object, right? If count the number of limbs, it was passed a pet object, and the method was invoked, count the number of limbs. It can go into the pet object that was passed and count the number of limbs. But in this case, it wasn't passed a pet object. How can it count the number of limbs when it's not passed a pet object? So what happens is that in C++, object-oriented languages in general, even though you don't pass it an explicit pointer here, explicit parameter, if it's an instance method, it gets an implicit parameter. It's passed in by the runtime system. It's passed in by the compiler. Automatically stuffs in the first parameter, which is not visible. You get a first parameter that is invisible. Okay, that first parameter is nothing but a pointer to the object on which you're invoked. Remember, it's not the object itself. It's a pointer to the object on which you're invoked. Okay, now here's a very interesting question for you. Why did the designers of C++ say that when you invoke an instance method, you would also get as an implicit first parameter a pointer to the object rather than the object itself? I'm passing it as I'm calling the instance method, and the instance method needs to work on an object. That object needs to be passed in as a parameter, an implicit parameter, so the user doesn't pass it. It's automatically passed in. So I have two options of passing the object in as a parameter. I could pass the object itself, or I could pass a pointer to the object. Yes? Yes or no?
Yes.
So why did the designers of C++ say when an implicit object needs to be passed, I'll only pass a pointer to the object, not the object itself? Why did they do that? There's a bunch of advantages in doing that, right? Because a pointer, the size, it's fixed. It's always 8 bytes or 4 bytes or whatever it is, right? So it's 8 bytes. So no matter how big the object, you're only passing 4 bytes for that first parameter, right? They could have enforced it and said, when you create an instance method, you got to explicitly pass a pointer to the first, to this object, And it's messy, right? So they say implicitly every instance method gets the first parameter free, whether the user passed it or not. The first parameter is free. It's given to you, and it is a pointer to the current object. Now, how do you refer to the current object? You know, they could have said, you know, there is no parameter here, no parameter, but you're going to get past an implicit secret parameter, and I'm going to call that secret parameter secret, right? And so, in fact, there is a secret parameter passed into this method, whether you pass it or not. So if you want to access that secret parameter, all you need to do is just say, you know, secret.num1 here, right? That way you can access that. However, what the designer said is that, you know, we're going to pass a pointer to the current object, and we're going to call that not secret, I'm going to call it this, right? And it makes sense, right? Because you're operating on this object. You got an object, and you're going to operate on that object. What is a good name for that object? It's this, right? So inside of a method, the object is basically called this through a pointer. So inside a method, if you see the word this, it is basically the formal parameter name, not the actual parameter, the formal parameter name for a pointer to the current object. Does that make sense?
So this is a formal parameter.
This is a parameter, right?
This is a parameter
Yeah.
that points to the current object.
Yes.
The pointer to the current object.
Yes, a pointer to the current object, right? Every instance method has only one current object, right? So the current object is only one because it's operating on one object. It's an instance. So the pointer to that object is implicitly available to you as this object. And never ever in your code do a delete this, okay? Because it's a pointer, you can delete it, especially if it's a dynamic node, like it was created new. And you do a delete this inside, you know, your stuff, okay? Don't do that. Yeah, that's another good rule of thumb to follow, is that you don't delete this. You know, you get out of the method and then delete the pet object. Don't delete the object inside of this, okay? Inside of the instance. Okay? Because, you know, when you delete the instance and you're still inside the instance method, what happens, right? Yeah, you're attached to something. You're attached to a castle, and the castle just disappeared. And you're gonna fall, you know, in the air. So don't delete this inside the method. Get out of there and then delete it. So those. But however, you can inside of a method you can say delete this arrow next. That's fine, right? This you can delete the next property of this object. You're not deleting this object. You're deleting the next property of this object. That's allowed. But you just can't delete this. Does that make sense? Anyway, you know, I can talk about this for hours on end. It will not make 100% sense until such time as you get bitten by it. Not even when you try it out. You know, when you try it out and it works, I feel really sorry for you, right? I feel sorry for programmers who get their programs working the very first time. Okay? No, it's it should fail. It should die in ways that it might otherwise die in users' hands. Okay, so you know what pitfalls you need to look out for, and then you know how to fix them, so that it doesn't die in bad ways in the hands of users. Okay, like I said before, if you gotta die on your own terms, right? So when when a user says, gives you a string when you don't expect a string, you expect an integer. Don't just throw up your hands and get killed by the operating system. Because if you don't know how to handle it, the operating system will kill you. Say, hey, you're writing into places that you're not allowed to, I'm gonna bam, knock you out, right? So that is dying not on your terms. However, catch the exception or whatever it is, right? Or don't say, I want an integer, but you gave me a string. I'm not able to handle that, so I'm going to go home. Later on, when you have an integer, call me, I'll come back and do your job for you. That is dying on your own terms. You say, I can't do this. I'm going to exit now. That is fine. But if you do crazy shit, then you'll get knocked out by the operating system. Okay. All right. So that's all there is to it. Pointers, and people talk about pointers. The only way you can get to know this intimately is to die in your programs. And not die. You write programs that crash because of pointer errors, right? You have to struggle. You have to struggle to debug your pointer errors. And if you have a pointer error, and I jump in and say, well, this is why it's going wrong, and then you look at it and say, yeah, oh my gosh, I could never have found that out myself. Thank you, Anand, for helping me debug the code and saying, oh, that pointer, that's where it is, right? Unfortunately, that solves your problem, but it does not really fix the real issue, right? Because later on, you'll come, to a similar situation, and your code won't work, and you won't know how to, because you haven't felt the bitterness, the sting, like Leonardo said, you gotta feel the sting of, damn, this is this one small bug keeping this beautiful product from coming to actualization, right? You gotta feel that, and when you feel that, you'll get a sense of how to fix pointer errors, right? So don't ask people to help you with pointer errors. Right? Sometimes you can. You're really banging your head on a brick wall. You don't know how to fix it. Then your best bet, if you're an experienced programmer, you should ask your colleagues for help with pointer errors, right? If you've been coding for a while and you're stuck with a pointer error, it doesn't matter at all. You can ask all your colleagues in neighboring cubicles, if they have spare time, come over here, pour over my code and tell me what the pointer error is. Where's my regular expression wrong, right? All those things you can do once you get experience. But during the time you're learning, don't ask people to come and help you, right? Because most of these people don't know how to help. They'll just tell you the solution. Even in our STEM center, right, with tutors, we actually screen our tutors. We teach them and train them and tutor them and tell them to never give the solution, right? Because tutors, if you think about it, for them it's a job to help you, and if they give you the solution, they've done their job, or they think they've done their job, right? Because you're not going to bug them anymore. And so natural response for any tutor, not at Foothill, even outside, right? Wisant, or go and get help from a tutor. You got to really select your tutor. They say, select your doctor, select your tutor, select your lawyer, right? You got to interview these people before you get their services. Because if you pick the wrong one, then you're the one who's, screwed, really, because they'll just give you the solution because they just want you out of their hair. That's not what you want, though, right? You want to know how to solve it on your own when those guys are not around. You don't want to go back to them and pay $60 each time saying, I got this problem, fix it for me, $60. No, that's what other people want. No, but you want to say, no, I'll give you $60, but don't fix it for me. But for all the $60, tell me how I can fix it myself. And very few people know how to do that. We teach people how to do that in the STEM Center, right? Our tutors, I don't know if they follow it or not, but they go to a training where we teach them, don't give the solution, right? Just give them little hints, just point them, make them suffer. Not suffer in a bad way, right? But make them struggle. It's not suffer, struggle. You gotta struggle. When you struggle, then what you get out of the struggle is yours forever to keep, right? When you get something easy, right? When your mom or dad says, here's a brand new iPhone 10X or 11X, right? You got that without a struggle. Yeah, it's not yours to keep because you don't appreciate it as much. Right? You don't get as much joy out of it. That's my feeling anyway, right? Maybe you get joy out of things that are given to you for free, but eventually you'll find, I think, that those are not as lasting as things that you create yourself. Because then you create something yourself, it came out of nothing. Because it came out of nothing, right? That's a feeling of true creativity. Right? Then you get to enjoy that, and other people will get to enjoy it too. All right, so that's basically it. I think is it time for? Do you want to code? Do we have time for coding?
It's about time.